Hello, can you hear me?
Yes, we can hear you.
Okay, and I can see you. Okay. Can you see the blackboard?
Yes.
Excellent.
Yeah, it looks very good.
Okay, so the camera is supposed to follow me automatically, but if there is any problem, please let me know and we will try to fix it. Okay?
Of course, please start.
Okay, so thank you very much. It's a very great honor to speak at the conference for N.K.Nikolski, and it is very difficult to overestimate the impact of Nikolski on my development. So my favorite book of Nikolai Kapitonovich is the book which is called Easy Reading. I have not found it very easy, but I have found it very inspiring. So for this inspiration, I'm very grateful to Nikolai Kapitonovich. So let us start. We will have occasion to refer to this book numerous times during the talk. So let us start with the standard sine kernel, which is written here, and consider the corresponding determinantal measure. Excuse me, запись идет, да? Да. The corresponding determinantal measure. So to each configuration, we assign the random entire function. The random entire functions. This is essentially analog of characteristic polynomial of a random matrix. In fact, a configuration which is just an infinite subset of the real line without accumulation points. So the configuration is essentially the scaling limit of the spectrum of a random matrix. And so this is the scaling limit. This statement can be made precise. This is scaling limit of characteristic polynomial. In fact, not of characteristic polynomial itself, but of a ratio of two values of characteristic polynomial. And in fact, it becomes especially clear if one considers a function of two variables, which we will have occasion to consider. We shall see that it is useful to consider z and w belonging to the upper half plane, and in fact it is useful to consider the upper half plane as the Lobachevsky plane, and Lobachevsky isometries will be important for what follows. Okay, so the corollary of, I should say that the abstract, there was an abstract which is in the booklet, but in fact I sent a new abstract already because I have proved a little bit more. So let me start with formulating the result as it is in the booklet. Here it is. So the result is the following, that almost every configuration with respect to the sine process is a complete set for the Pelley-Wiener space, is a complete set for the Pelley-Wiener space plus one particle. So this plus one particle is what I say by saying that it has excess 1. So it's complete set for Pelley-Wiener space plus one particle. So why? So let me say that the fact that it is a complete set, so almost every configuration is a complete set for the Pelley-Wiener space. It's a theorem, in fact, of Gauche, of Supraschecker-Gauche, and it also holds for very general determinantal point processes, all determinantal point processes. This is a result by Yan Tsiu, Alexander Shamov, and myself. But, so it is always a complete set. But it is not always true that it admits a minimal subset. And of course, it is a separate question, even if it does admit a minimal subset, which is not always true for determinantal point processes, that how many particles does one need to take away? So in fact, for the specific case of the sine process, the answer is that it is precisely one particle. Precisely one particle. Okay, so this is the corollary of the main result, and this is the main result, so it is new. Just the result is the following, that in fact the reason, so one can ask the reason, why does this configuration, why does it have excess 1? So the fact that the configuration is complete is essentially equivalent to the statement that this infinite product is not in Pelley-Wiener space. This function, when t belongs to the real line, is not square integrable. It's not square integrable. If it were square integrable, then it would be a zero set, but in fact, once it is not square integrable, it also follows by there is a separate argument that the X is a uniqueness set for the Pellev inner space. So now we remove one particle. So P in X. We remove one particle, and we ask ourselves, what about this function? Does it belong to L2? So in fact, it does not belong to L2, and there is a reason why it does not belong to L2. And the reason why it does not belong to L2, this is precisely the main result of the talk, which please allow me now to formulate, is that this random measure that is written on the blackboard, it's a random measure on the unit interval. It's the random measure on the unit interval. So I take this function. So again, it is important to think about the upper half plane as the Lobachevsky plane. So W goes to the absolute. So this, well, the formula is written. This specific random measure, in fact, converges to Gaussian multiplicative chaos, to the very standard Gaussian multiplicative chaos of Jean-Pierre Cahn with a standard kernel with a logarithmic singularity on the diagonal. So of course, if it converges to a random measure, then it cannot be square integrable because in fact the L2 norm grows linearly. So it is not possible. Okay, so this much for the main result. And now let me explain how the argument works, and in fact the second theorem of Séguin will play a very important role, and the second theorem of Séguin will play a very important role, and in fact what will be important for me are the additive functionals of the sign process. So I consider sums over particles. Sums over particles of functions, of values of a function. Obviously, clearly, the logarithm of my random entire function. Let me put it down a little bit. So the logarithm of random entire function is particular case of such additive statistic, and in fact, these additive statistics behave very much as normal random variables. So much it is true that there is a theorem of Soshnikov, central limit theorem of Soshnikov, limit theorem of Soshnikov. In fact, the analysis of Soshnikov builds upon the work of Johansson also. So Johansson, who considered the random unitary matrices, the random unitary matrix sampled according to the Haar measure and proved central limit theorem there. But Soshnikov proved the following theorem. Soshnikov says that if F is in the Sobolev space H1/2, and please allow me, in order to fix notation, please allow me immediately to write that I will very frequently use the H1/2 semi-norm. H1/2 semi-norm. I will use it very frequently. Okay, so yes, so just Soshnikov takes a function in H1/2, considers the additive functional SF, and then applies scaling transformation with parameter R, SFR, and this function converges in law to the normal law with law precisely the Sobolev 1/2 semi-norm over 4 pi square. Sobolev 1/2 semi-norm over 4 pi square. Okay. This is the central limit theorem of Soshnikov. In fact, the central limit theorem of Soshnikov proceeds by proving, there are various ways. The specific argument of Soshnikov proceeds by estimating cumulants, but other arguments are also possible. So proceeds by estimating clearly the exponential moment of this additive statistics. And so the exponential moment of this additive statistics is precisely the key object of this talk. So in the case of random unitary matrices, if I were estimating if X, instead of point configuration, if X were the spectrum of infinite unitary matrix, then this expectation, so here I write expectation with respect to the sign process of the exponential moment, if I were considering not the sign process but the circular unitary ensemble, so that is to say the X would have been the spectrum of a random unitary matrix distributed according to the Haar measure, then this would be just Fredholm determinant with symbol lambda f, and Topliss determinant with symbol lambda f, and I would be able to use the second theorem of Séguin, except that the theorem of Séguin is not good enough for my purposes, in that I need not the second theorem of Séguin itself, but I need also the error term in the second theorem of Séguin, and so I need, in fact, the formula of Borodino-Konьков-Geronimo case. The formula, which I will now recall directly in my setup. So the formula of Borodino-Konькov-Geronimo case. So it was discovered by Geronimo case in '79, but the result was then rediscovered by Borodino-Konькov in 2000, and then the initial paper of Geronimo case was rediscovered. Okay, so the formula of Borodino-Konькov-Geronimo case, in fact, gives the second theorem of Séguin with error term, and therefore it is possible to take directly the scaling limit in this formula, and so it is the scaling limit that I will now write. So I will write now that the exponential moment of lambda SF is, of course, so first we have the first Séguin theorem. Then we have the second Séguin theorem. And now we have the term of Borodino-Konькov. Let me write it. So the determinant of 1 minus... okay, I should write a little bit smaller. Otherwise the term will not enter. So, okay. So I have the first Séguin term, then the second Séguin term, and now there is a determinant of a Hankel determinant, which after taking the scaling limit takes this form. So this is the continual Hankel determinant. A continual Hankel operator, I will introduce the notation in a moment. So just, okay, so just f is f plus plus f minus, the projections on the positive and the negative Fourier frequencies. So h minus plus is 1 over 2 pi exponential f minus f plus, and h plus minus is the same thing, but reversed and with the tilde, exponential f plus, where the tilde as usually stands for the reversing of Fourier frequencies. Okay, there we go. And the my attempt at writing the Gaussical H stands for the following. Okay. So, and this is the scaling limit. This is the scaling limit of formula of Borodin-Okounkov-Geronimo case. Here it is. This is the scaling limit of the formula of Borodin-Okounkov-Geronimo case. So this formula immediately gives me. So here immediately gives me the normal approximation. In particular, the central limit theorem of Soshnikov is a direct corollary of this formula. In that this term, since I'm cutting the frequencies, since I'm cutting out the low frequencies, this term is governed by the Sobolev 1 norm, not the Sobolev 1/2 norm, but in fact the Sobolev 1 norm, not even the Sobolev 1 norm, but the Sobolev 1 semi-norm. So the Sobolev 1 semi-norm. So just the Sobolev 1 semi-norm. And so in particular, when I am doing the scaling transformation like this, this term goes to 1. This trace converges to 0 and this term goes to 1. So f, yes, so this is just the only thing that I need, just to establish the central limit theorem of Soshnikov from this result. But in fact, so from this quite general analysis, I would like now to go to very special linear statistics and precisely to logarithms of the random entire function that we had before, to logarithm of the random entire function gx. Here it is. To the logarithm of the random entire function gx. Okay, so let me now write SZW is just the additive statistic sum over x and x of logarithm x minus z minus logarithm x minus w. Okay, so and now proceeding from the Soshnikov central limit theorem, let me assign to this SZW a Gaussian random variable, whose, so I consider now, okay, let me go here. Just a moment. I consider now a Gaussian, consider a Gaussian field, a Gaussian, in fact, consider a Gaussian process, if you wish, a Gaussian process. This is a key step. YZW. So Z and W are in the upper half plane. So in essentially the Lobachevsky plane. We shall see why I insist on this. In fact, I can say right now because we will see that the Gaussian process will be invariant under Lobachevsky isometries. So this YZW, as one can see from the formula for SZW, I lift it a little bit from the formula for SZW. YZW satisfies the cocycle equation. And the expectation is 0. And the variance is precisely the Sobolev 1/2 semi-norm of this quantity, but in fact, so I can write it. It is just the logarithm of 1 plus cosine hyperbolic distance ZW over 2, where distance is the Lobachevskian distance. Scan distance. And just we can write a formula for that. Okay, let us see. I wanted to write it up. Just 1 second. So dZw. So in fact, cosine hyperbolic of dZw is 1 plus z minus w squared twice imaginary part of z, imaginary part of w. Here we go. Here we go. Okay, so here I have described, okay, let us go, actually maybe go down with this one. Here I have described a Gaussian process. By its very definition, again, by its very definition, this Gaussian process is invariant under Lobachevsky isometries. This, so S, Z, S, R, Z, RW, by the theorem of Soshnikov, converges in law to YZW. So this is Soshnikov. This is Soshnikov. This is Soshnikov. So SRZRW converges in law to this. So let us look at, let us draw a picture. So I can consider Lobachevsky plane. So, and here I have an observer. So here I have an observer in fixed position, let's say at 0. So on the upper half plane. So I switch between the upper half plane in the disk, because so it's more useful for me to draw pictures in the disk, because like this is the fixed observer. Otherwise I would have to place the fixed observer at I. So then I have an arc of the horocycle, and the arc of the horocycle converges to the absolute. Converges to the absolute. So the arc of the horocycle converges to the absolute. So these Gaussian random variables clearly from the very formula, as Z stays fixed, this is my Z, the position of my observer, it stays fixed, and W moves to the absolute, the variance of the Gaussian random variables goes to infinity. At the same time, the variance goes to infinity. At the same time, the covariance does not. So the covariance, as these points converge to the absolute, the covariance stays bounded. In fact, two geodesics in hyperbolic space, not necessarily on Lobachevsky plane, in any hyperbolic space in the sense of Gromov, two geodesics for sometimes they go together and then they diverge, and the triangle inequality essentially becomes equality. So this is the behavior. So all triangles are thin in hyperbolic space. And this is completely general statement of any hyperbolic space, and of course also in Lobachevsky plane. So, but just precisely the covariance, it is this part. It is comparable. So one can see that for large values from the formula, one can see for large values of the distance, the variance of my Gaussian random variables is comparable to the distance itself. So this field in the large, grossièrement, in the large, this field is similar to the Lévy field, though it is not a Lévy field, but it is quite similar. So the covariance is comparable to the Gromov product, in fact. So distance Z U plus distance ZW minus distance UW over 2. So, but this means, in fact, that it stays bounded. Even as the points diverge, the Gromov product stays bounded. And so, these random variables, their exponentials, of course, converge to the Gaussian multiplicative chaos. So it follows from, so even from theorem of Kahan, from any of your favorite theorem, it follows that e to the random measure e to the y I, let me write it like this, I 1 plus t plus eps plus I over r. So please observe that here I have divided by r. I have divided by r, but on the level of the y's, it has no importance because the Gaussian process of y's is invariant under Lobachevskian isometries. So I have, but here I have divided by r. So I have 1 plus t plus I over r. Okay, so this one divided by its expectation. Divided by its expectation. The expectation is of course nothing but the exponential of the half of the variance. And I can also put a gamma here for suitable values of gamma. So this of course converges to GMC. This of course converges to Gaussian multiplicative chaos. If you wish, this is the definition of Gaussian multiplicative chaos. dt, this times dt, this times dt. This is definition of Gaussian multiplicative chaos. This is the exponential of Gaussian process for which variances explode, but the covariances converge, and it converges by the theorem of Kahan. It converges to the Gaussian multiplicative chaos. Please observe, however, that here I am not in a setting of Kahan. I am not in Gaussian. So convergence. So let me try to say it in the following way. So the additive statistics, when it is expanded, it becomes Gaussian. But these are two different convergences. So first I expand and then I go to the absolute. So for the Gaussian field, convergence to the Gaussian multiplicative chaos follows from standard theory. But I want convergence of Gaussian multiplicative chaos to converge to Gaussian multiplicative chaos of these expressions, which are not Gaussian. These are not Gaussian random variables. So there is a deviation from Gaussianness. So here it is. There is the non-Gaussian term, the term of Borodino-Kunikov-Geronimo case. So the key point in the argument is an estimate of this term. So that this term, in fact, disappears from the matrix of covariances. I should also say that from the technical standpoint, what is very convenient to me is not the original approach of Kahan, but in fact the approach of Berestitsky, which is based on the theorem of Girsanov. So on the theorem of Girsanov. So it is possible, because Berestitsky uses L2 approach for convergence of these random measures. He operates in L2, but he needs, so to speak, to cut away the very high values of the function, so of this function gx, for example, he needs to cut them away. And for this, he uses an analog of the theorem of Girsanov. So, and it is possible to carry over this argument. And in fact, I am greatly helped in that by the following estimate that I have for high frequencies. So please observe that this estimate, the estimate of Borodino-Kunikov-Geronimo case, the scaling limit of the estimate of Borodino-Kunikov-Geronimo case, is very convenient when lambda is real. We assume that the function f is real. When lambda is real, then clearly h minus plus and h plus minus are functions of absolute value 1. So these are fast oscillating integrals, and this determinant is, to say the least, less than 1. Whereas on the other hand, if lambda is imaginary, then these functions now become, by the way, I forgot to put a lambda, please excuse me. I forgot to put a lambda here. So please excuse me, a lambda of course. if the function is imaginary, if lambda itself is imaginary, then these functions become real. So this term explodes and it is difficult to control it. So, but in fact, I have an estimate, and this is what I would like to formulate now and maybe close with this. So I have an estimate. I have an estimate. So estimate on high frequencies. Estimate on high frequencies. Estimate on high frequencies. Estimate on high frequencies. So in fact, if I have estimate exponential of e to the I lambda SF, then I can prove that this quantity is less than exponential minus a certain epsilon, absolute value of lambda, epsilon value of lambda f 1/2 square plus gamma square lambda square. So this estimate works, as one can see, for lambda all the way up to the Sobolev semi-norm of f. And this estimate, the argument and the proof of this estimate here, again, I follow an idea of Johansson. The way of proving this estimate is by using the fact that the sine process is quasi-invariant. Sine process is quasi-invariant under compactly supported diffeomorphisms of R. Compactly supported diffeos of R. And as a final remark, let me just say that this fact that the sine process is quasi-invariant under compactly supported diffeos of R also allows us, in joint work with Borichev and Klimenko, just to obtain also an interpolation result for the Pelle-Wiener space. So we know that the sine process has access 1. So the realization of sine process without one particle is complete and minimal set. Is it possible to recover a Pelle-Wiener function from the configuration of the sine process? And in fact, in joint work with Borichev and Klimenko, we proved that if the function f is in Pelle-Wiener space and decays sufficiently fast at infinity, so just is an L2 is an L infinity, just for sufficiently high n, and we didn't try to obtain optimal value of n, then in fact the Lagrange formula recovers f. The Lagrange formula recovers f. The main technical difficulty in this result, this joint result with Borichev and Klimenko, being the estimate of the contribution of this function gxp when some particles come close together, when there are some accumulations of particles. It's an event of low but positive probability that particles come close together, and this is the main difficulty in obtaining this. But in fact, we use that the sine process is invariant under compactly supported diffeomorphisms. So in fact, our result works. This result works also for Airy, Bessel, and Fogg. But in some sense, it is conditional. So let me just say. So for Airy, Bessel, and Fogg, it is possible to prove the analog of such result, but without the word 1. It is possible to say 1 or 2. So for Airy and Bessel, it's 0 or 1, and for Fogg, it's 0, 1, or 2. But conditionally upon the end, in fact, this axis being a tail satisfying to the Kolmogorov 0, 1 law, this axis is almost surely constant. in virtue of the Kolmogorov-0,1 law. So just the interpolation works, so to speak, conditional on this result for processes with finite access. But for the sine process, the result is precise, x is equal to 1, and the reason for this is that the characteristic polynomials converge to the Gaussian multiplicative case. Thank you so very much.
Okay, thank you very much, Professor Bufetov. Are there any questions? Any questions on Zoom? Okay, if not, so let's thank Professor Bufetov again.
Thank you very much. Thank you very much.